The broadcast is now starting. All attendees are in listen-only mode.
Welcome everybody to our webinar on modeling manufacturing processes with COMSOL Multiphysics. My name is Ksenia Simina. I'm a marketing executive at COMSOL UK. In this webinar, you will learn why it's important and how to simulate manufacturing processes using multiphysics simulation. Our speaker today is Robbie Balcom, who is the technical director at COMSOL UK. Robbie graduated from the University of Strathclyde in 2007 with engineering degree in aeromechanical engineering, and then carried out his PhD in the area of numerical modeling of rolling contact fatigue at Imperial College London. Before we start, I'm going to briefly run us through some introduction to the GoToWebinar software in case you haven't used it before. You can see a control panel on the right-hand side of your screen. Please use questions pane to submit any questions as they arise during the webinar by just typing them in a box. Your answers won't be displayed. Instead, towards the end of the webinar, about 30 to 35 minutes in, Robbie will answer the questions that have come in. Please don't miss out on this opportunity and submit your questions early. We'll try to answer all your questions, but any we don't answer will be followed up afterwards. Everyone will receive an email within 24 hours with a link to the recorded event, so you and your colleagues can watch the webinar on demand. Okay, enough intro information. I'm going to hand over to Robbie. Please take over, Robbie.
Thank you, Ksenia. Thank you for joining me for this webinar this afternoon, Modeling Manufacturing Processes with COMSOL. So first of all, what I'll do is just very quickly go through the agenda for the webinar this afternoon. So what I'm going to do to begin with is just give you a very brief introduction to COMSOL Multiphysics just to set the scene. And then what I'm going to discuss is kind of some of the modeling features contained within the software that I think are relevant to the topic that I'll be discussing this afternoon. So I'll cover some features related to solid structural mechanics modeling, electromagnetic modeling, and heat transfer modeling, and try and put these into the context of modeling manufacturing processes. And then towards the end of the webinar, I will do a live demo where I'll set up and run a simulation of a metal solidification process, and then we will have a short Q&A session, and then Ksenia will provide you with some information on how you can find out more about COMSOL Multiphysics. So first of all, I just really want to introduce COMSOL Multiphysics itself. So COMSOL Multiphysics is a simulation tool for building and running simulations that combine different physical phenomena, but also for developing modeling apps that can be developed using the integrated application builder. So I would say that the traditional approach to numerical modeling involves partitioning the full spectrum of physics into smaller areas, such as heat transfer, structural mechanics, acoustics, and so on. However, very often, if you want to simulate a real system, it doesn't fit into one of these categories. So at COMSOL, what we adopt is what we call the multi-physics approach to simulation. So this means that we provide a modeling platform that allows you to combine different physical effects in a single model, in a single modeling environment. The idea here is to be able to improve the quality of your simulations by accurately reproducing the real system, but in a computational environment, by accounting for all of the relevant physical effects and physical interactions. So that might be involving something where you're combining heat transfer and structural mechanics to look at the effect of heat being applied to a material. Either it's changing the mechanical properties of the material, or perhaps it's also causing some thermal stress and strain within that material as well. Now, the software itself is a modular product. So we have the core module, which is called COMSOL Multiphysics. And this contains kind of core technologies such as geometry tools, meshing tools, solvers, and also provides a limited amount of modeling capability in the different application areas. There are also a number of modules developed for specific applications that are intended to extend the capability of the software. And these are categorized here in kind of 4 key sections. So we have electromagnetics, fluid and heat, structural and acoustics, and chemical. We also have some multi-purpose modules, which are for doing things like mathematical optimization. And there's interfacing modules that allow you to connect COMSOL either to CAD or to something like a scripting environment such as MATLAB. Okay, so in terms of kind of focusing on the topic today, I kind of wanted to start just by going through a case study. So this is a story that the manufacturing technology wrote for us, which is related to manufacturing. So they have used COMSOL Multiphysics along with the application builder to use simulations to develop and optimize an additive manufacturing process. Now, the simulation here combines changing geometry, heat transfer, and solid mechanics to predict the residual stress and the deformation in a finished part that has been manufactured using something similar to a 3D printing process. So the part is built up in layers, and this process can lead to deformation of the final part, which of course is something that's unwanted. So by better understanding this process, by running simulations, they can try and mitigate the amount of deformation in the finished part by adjusting the operating conditions or by making adjustments to the design, which will ultimately lead to a better, final product. Now, the simulation in this case has actually also been converted into a simulation app, which is what you can actually see in the image on this slide. So the simulation app presents a stripped down user interface that a app developer can distribute to allow designers to make design adjustments and build this into their design without having to consult a simulation expert. So you can see here in the image that a designer could do tests of the simulation using the simulation app to determine what the final part will look like and make changes to the design or the operating conditions to avoid an unwanted outcome. So I think that for a lot of simulations of manufacturing processes, one of the key results that is of interest is residual stress and deformation of the finished part or the finished item. And of course, structural mechanics is integral to these simulations. Now, COMSOL Multiphysics contains a broad set of functionality within structural mechanics that includes different types of studies such as static analyses, time-dependent, frequency, domain, eigenfrequency, and so on. And it also covers a wide range of needs, such as things like mechanical contact, large deformation analysis, nonlinear materials, and as well some multiphysics couplings, such as thermal stress, as I've already mentioned. As well as that, one of the key features and one of the nice features, I think, about the software is the ability to specify user-defined inputs. So this might be to define a user-defined material model, or more straightforwardly, it might be simply to define a user-defined boundary condition, to define some kind of time-varying load. And I think that this is one of the kind of key strengths of COMSOL Multiphysics. So looking now kind of more at the kind of material models. Now, there are a wide range of different material models available in COMSOL Multiphysics for modeling mechanical problems. And these will tend to be categorized as either linear or nonlinear in terms of kind of the relationship between the stress and strain. So in kind of the linear regime, we have sort of linear elastic, linear viscoelastic, and also some multiphysics material models such as piezoelectric materials and magnetostrictive materials. I won't be covering them in much detail today, but I'm just going to say that a colleague of mine is running a sensors webinar soon, and if you're interested in learning more about that, I suggest that you sign up for that. Now, in terms of kind of nonlinear material models, they can kind of be split into two groups, structural and geophysics. Now, for today's webinar, I'll really only be focusing on a couple of the structural material models that I think are actually relevant. So, in terms of kind of nonlinear material effects, you can, of course, model elastoplasticity to allow the material to yield where it transitions from being elastic to elastoplastic. So this allows you to model the post-yield behavior where the material is permanently deformed and doesn't return to its original shape. So this would be relevant if you were looking at, for example, a metal forming process where you are modeling a purely mechanical process and forming the shape of the part through the mechanism of elastoplasticity, by punching it out. We also have strain rate dependent kind of viscoplastic material effects that can be modeled using either viscoplastic or creep material models. And this is an effect that's usually driven by heating or can be driven by a combination of thermal and mechanical loading. And it can be characterized as a solid behaving somewhat like a highly viscous fluid, where the solid material actually flows or creeps. Now, this again is something that's seen in manufacturing processes, for example, in spark plasma laser sintering, where a current is used to generate a heat via Joule heating, and the powder will behave somewhat like a fluid, and it's also seen in some additive manufacturing processes where material is being deposited at very high temperatures. Now, the last kind of material model here that I wanted to kind of pick out to explain in more detail is porous plasticity. So this extends the elastoplastic functionality to porous materials or powders to allow powder compaction processes to be simulated, for example. This type of material model can be used to track the porosity of the material during the compaction. So for example, if you have a metal powder which is in a die that is being compacted through an applied pressure that's applied by a punching tool, while this process is being simulated, and the porosity of the powder is decreasing, the density and the strength of the material is increasing, you can actually track the porosity during this process. And these types of material models are important because they allow you to accurately compute the final porosity of the material once this compaction process has been completed. So, as I mentioned at the beginning, kind of one of the key sort of aspects of the software is this idea of multiphysics. So within the kind of realm of structural mechanics, there are a number of multiphysics couplings that are available. This is just some of them. Now, the one that I guess I'm going to focus on here is thermal stress. So, I mean, one of the key mechanisms that is simulated in manufacturing processes is thermal stress. And this is driven by thermal expansion, which is the tendency of a material to change in shape, area, and volume in response to a change in temperature. So when a material is heated, the kinetic energy of its molecules increases, therefore the molecules begin vibrating and moving more and maintain a greater average separation, and hence you have a change in volume. Now, the software has a predefined interface for modeling the coupling between heat transfer and solid mechanics to easily set up this type of thermal stress analysis. And you can also actually incorporate a temperature coupling that allows you to capture the effect of the change in temperature on the mechanical properties of the material. Of course, the temperature dependence itself has to be specified, but this helps to capture that coupling so that you can see the effect that the temperature has on, for example, things like Young's modulus and so on. So this kind of ties into what I was talking about in the previous slide. So in terms of looking at nonlinear material effects, you can easily account for multiple, I guess, nonlinearities when you're defining your material. So rather than perhaps just specifying a material in terms of a stress-strain relationship, you could also incorporate temperature, so that rather than having a curve, you actually have something that is a stress or is a surface. So you can easily account for things like the effect of temperature on the mechanical properties of the material. And as I mentioned, we also support a number of nonlinear effects that are driven by heating, such as creep and viscoplasticity, things that are observed in manufacturing processes, and also in other simulations, like looking at solder, for example, as well. And when it comes to looking at these nonlinear material effects, you can actually combine more than one material effect within a single domain of the model. So you can actually look at the effect of both elastoplasticity and creep within the same material, because you might be looking at a simulation where you have high values of stress, so you have a transition from elasticity to elastoplasticity, but you might also be adding heat and looking at the process over a period of time, and therefore you may also need to account for creep in the simulation as well. Now, one of the features which is actually new for 5.4 is the material activation and deactivation feature. So when modeling a manufacturing process like 3D printing, the geometry of the final part will tend to be built up in layers. So as each layer of material is deposited on the last. So this new feature added for the latest release can help with simulating this process, because it allows you to birth material in an unstressed state, so that you can add layers of solid to the existing layers of solid material in a consistent way. So you can actually compute the transfer of stress correctly from the existing material to the new material that's being deposited. This will often be driven by the fact that the material is deposited at a high temperature, and the different layers are contracting at different rates as they're cooling. So kind of moving on now to electromagnetics. So I guess the relevance of electromagnetic modeling to manufacturing processes may not be as immediately clear as it is for structural mechanics. However, electromagnetic methods are often used to heat the material in a manufacturing process, whether it's induction welding of composites, induction heating of wires to make steel rope, joule heating of powder and plasma sintering, or a laser sintering process. In all of these, electromagnetism plays a part. So COMSOL Multiphysics kind of covers the full electromagnetic spectrum, from static simulations where you're looking at DC currents through low frequency simulations all the way up to the high frequency end of the spectrum. So we have modules to cater for DC currents at the low end of the spectrum, as I mentioned. If you're looking at kind of in the middle of this electromagnetic spectrum, where you might be looking at something like microwave problems, or at the high end of the spectrum where you might be looking at something like a laser or laser heating. And for each of these sections of the electromagnetic spectrum, we also have couplings that allow you to easily set up a coupling between the electromagnetics and the heating to look at the electromagnetic heating. So these couplings will tend to convert the electromagnetic losses either to resistive effects or absorption to a heat source that can easily be used to model the heat transfer. So this might be looking at joule heating, which is based on a resistive heating effect. It might be induction heating, or it might be microwave heating. I should also add, actually, that we also have a coupling that allows you to look at laser heating problems as well. So that kind of takes me on now to the heat transfer modeling. So I guess this is kind of the last branch of physics that I wanted to kind of discuss. So COMSOL supports heat transfer modeling by the three main mechanisms of heat transfer. So you can look at heat transfer by conduction, convection, and radiation. So of course, thermal conduction is where you're looking at the transfer of energy within a rigidly bonded material from an area of high temperature to low temperature. And the rate of conducted heat, or the flux, is proportional to the temperature gradient and the thermal conductivity of the material. The convection or convective heat transfer tends to involve looking at particle movement. For example, the movement of fluids, where the convective heat transfer is usually driven by heat being carried by a fluid from an area of one temperature to an area of another temperature. So that will tend to be the dominant form of heat transfer in liquids and gases. Of course, conduction is the case for solids. And this can be modeled as well. It can be modeled as a coupling between CFD and heat transfer. So you can actually look at things like forced convective flows, where you're using some fan or something to drive the flow, but you can also look at things like natural convective flows, where you have a circulating flow due to a density change, or density gradient, I should say, in the material due to the effect of buoyancy. And of course, you can also model radiation. This can be looking at radiation from a hot object into the ambient environment, or you can look at radiation between two different objects, and you can also actually look at the absorption of heat through radiation in semi-transparent media as well. So within the heat transfer module, again, there's a number of multiphysics couplings. Now, I'm not really going to go into too much detail on these because I think I've mentioned most of them already. So we have the electromagnetic couplings, the coupling to stress, and there's also couplings to fluid flow as well, for looking at things like, in this case, it's moisture transport, but also if you wanted to look at convective heat transfer as well. Now, there is one sort of feature that I just wanted to highlight here that's in the heat transfer module, and this is the deposited beam power feature. And this is intended to make simulating laser heat sources very straightforward. So the user can select a laser profile. So that could be Gaussian or top hat, a laser spot size, the power of the laser, and the orientation. And as you can see from this slide, this can actually easily be set up as a moving heat source using some time-varying function. So this could easily be used to model something like a laser additive manufacturing process. And my colleague Walter Fry actually recently wrote an interesting blog about defining a laser path on a flat plate. And this blog's available on our website, actually, if you want to read into this in more detail. Okay, so this takes me on to the demo. So the demo model that I'm going to set up is a solidification of a metal, or that's the title of the model. So what I'm going to simulate here is the solidification of metal where there is a liquid-solid phase change occurring. So what you can see on the slide here is we have this column of metal which is flowing. It enters at the top as a molten metal, but as it flows down the column, it cools, and as it cools, it changes from a liquid phase to a solid phase. Now, the model that I'll set up will demonstrate how to look at or how to implement a phase change process in COMSOL, but I will also show some other useful features, namely setting up a load ramp and also how to use adaptive mesh refinement. In this case, the adaptive mesh refinement will be used to refine the mesh at the phase front where the solidification occurs. So in this region in the slide here. So in terms of kind of modeling heat transfer with phase change, the software has a predefined phase change feature that is within the heat transfer module that allows you to easily set up this type of problem. The feature itself is based on defining a melting temperature, which you can see here. So this is set up for a transition from water to ice or vice versa. So the temperature here is 0 degrees. So you would specify the melting temperature, a transition interval, so the temperature interval over which the phase change will occur, and also the latent heat. This is used to consistently account for the thermal energy that's consumed during the phase change process. So in summary, the method that we're using here is called the apparent heat capacity method. So this defines, as you can see here on the slide, on the graph that's shown, defines a smooth transition between the two phases over a specified temperature interval that sits on either side of the melt temperature. And the specific heat capacity is added to the heat capacity at constant pressure to account for the energy required to cause the phase change process itself. And for my particular problem, I'll be looking at something like this, where I have a solid to liquid phase. Okay, so I'm going to come out of the slides now, and I'm actually going to move across to the software. Okay, so first thing I'm going to do here for my demo is I'm actually going to select here the option Model Wizard. Okay, now the geometry that I'm modeling is cylindrical in shape. So what I'm actually going to use here is I'm going to use 2D axis symmetric as the space dimension, and this is assuming that I have a rotational symmetry, which is the case for a cylinder. So I'll select 2D axis symmetric. Okay, the next thing that I need to do here is to choose the physics that I want to simulate. Now, I could select here a number of different physical effects to include in my model, but I'm actually only going to add heat transfer and fluids for this problem. I'm actually going to model this purely as a thermodynamic problem. So I'm going to add heat transfer and fluids. Okay, and the next thing I need to do is to choose a study type. Now for this problem, I'm actually going to compute this as a stationary problem. So I'm actually going to compute the stabilized temperature of the material rather than looking at how it's varying in time. So you can think of this as the thermal equilibrium. So I'm going to add stationary here and then select done. Okay, so now that I've made those selections, it now brings me to the user interface of the software here. So you can see here I have a model builder, and this has kind of the modeling steps that I need to follow in order to set up and run my simulation. So the first thing that I'm actually going to do here is I'm going to load in some parameters that I've prepared to save me having to type them out, given the time constraints. So I have some temperature inputs that I'm going to use for the model and some material properties that I'm going to use. So the next thing that I'm going to do here is I'm going to build the geometry. So I'm going to build the geometry in two sections. So both of these are going to be cylindrical. So in 2D axis symmetry, that is a rectangle. I'm going to specify the dimensions as the radius and the height of the first. Okay, and then I'm going to add a second rectangle with a radius and a height. And I'm going to sit this one on top of the first one that I've created here. Okay, so what I've created here is I've created two sections. The first section here is the section where the material will be contained within the mold. And then below this line will be the section where the material is actually come out of the bottom of the mold and is being cooled by some spraying fluid. So what I want to see is that the material has solidified before it exits the mold, or sufficiently solidified when it exits the mold. Okay, so I've got my geometry. I'm going to move on now to setting up the materials. So I have to define two materials here, although in effect I'm actually only modeling one material. So I'm going to specify the solid phase of the material and the liquid phase of the material. So when you're adding materials here, you can select to add a material from our predefined library of materials, or you can actually instead define the material yourself, which is what I'm going to do in this case. So I'm going to add two blank materials. And I'm just going to start by assigning material 1 to the top of the geometry and material 2 to the bottom. Okay, so I have to specify some parameter or some material inputs here, I should say. And these are based on the physics that I've selected, so I have to specify the thermal properties. So material 1, I'm going to call liquid. Okay, and the thermal conductivity here is 150. The density is 8500, and the heat capacity at constant pressure is actually defined here as a parameter. So I can actually just copy this parameter and use it here. And the ratio of specific heats here is 1. So that's my liquid phase defined. I'm now going to define my solid phase. So my solid phase has a higher conductivity than the liquid phase, so it's going to be 300. The density is the same. It has a different heat capacity at constant pressure, so I will add that. But it has the same ratio of specific heats. Okay, so I've added my materials. Now, the next thing that I'm going to do here is I'm going to set up the physics of the problem. So what I'm going to simulate here is I have a column here of fluid that's entering through this top boundary and exiting through the bottom at a velocity that I'm going to specify. So the velocity is defined here as a parameter. So this is the feed speed or the casting speed. So it's going to be 2.5 millimeters per second. Now, I'm not going to simulate the flow here, but I could extend the model to actually model the flow. I'm modeling a somewhat simplified version of this process. Okay, so here I'm going to first of all just specify the velocity, and it's going to be moving in the negative z direction. So I'm going to say here minus v underscore cast. So that's the velocity that the fluid is moving. The next thing that I'm going to do here as a subnode to the fluid is I'm going to add that I want this fluid to be defined as a phase change material. Okay, now in the settings for this phase change material, I need to specify the melt temperature. The default settings here are for water. So my melt temperature is 1356 Kelvin. So I'm just going to copy that and paste it into the box here. So I've defined my melt temperature. I'm going to specify the transition interval. So this is the temperature interval over which the material goes from phase 1 to phase 2. So I'm going to specify that as 50 Kelvin. This is going to be the initial value at least. Okay, and then here I'm going to specify the latent heat of the material, which again I have defined here as a parameter. So I'm going to copy that into the box. So I've specified the melt temperature, the transition region, and the latent heat of the material. The next thing that I need to do here is I need to specify the two phases. So I'm just going to reference now the materials that I've defined. So phase 1 is going to be my solid phase, and phase 2 here is going to be my liquid phase. And if I click on the material now, you can see that it's referencing the properties that I've defined here. Okay, so I've defined the casting speed or the velocity that the material is moving, and I've specified the phase change material definition. What I'm going to do now is I'm going to specify some boundary conditions to the problem. So a temperature here as it enters, which I will define using an inflow. So I'm specifying here the temperature of the molten alloy as it enters. And again, I have a parameter that I've used to define this. So this is 1200 degrees Celsius. Okay, so I have my inlet condition here specified as an inflow condition, and then I'm going to add an outflow condition at the bottom, and this is where the fluid is convecting the heat away. So I have my inflow here and my outflow here. Now on the solid surfaces, I'm going to have some heat loss to the mold here on this boundary, so some kind of steel mold, and then on this boundary here, what I'm going to do is have heat loss through radiation to the ambient environment, but also some cooling effect due to some coolant being sprayed on the material. Okay. So to do this, I'm going to start just by adding the heat loss to the mold here as a heat flux. And I'm going to set this up as a convective heat flux using a heat transfer coefficient and an external temperature. That would be the temperature outside of the domain that I'm modeling, or the ambient temperature. So I have my heat transfer coefficient here, which I'm again just going to paste. And my ambient temperature here is 300 Kelvin, which again I've defined as a parameter. And I'm going to assign that to the model here. Okay. I'm going to add a second heat flux condition on the lower part here, and this is the heat loss due to spray cooling. Okay, so I'm using a different heat transfer coefficient this time. It's much lower, but I'm using the same temperature. Okay, and then finally what I'm going to add here is I'm going to add some radiative heat loss using what's called surface to ambient radiation. So I'm going to add that here to this section of the model, and I'm going to define this in terms of an emissivity, which I have here 0.8, and also again in terms of the ambient temperature. Okay, so in terms of setting up my heat transfer problem, that's everything defined. I've specified the velocity that the fluid is moving. I've defined that this is a phase change domain, which means that either part here could be solid or fluid, even though I've identified them as liquid and solid here. I've specified the temperature as it enters. I've defined this outflow condition here where the fluid leaves, and I've defined some heat loss from the molten or solidifying material to the surrounding environment. So the next thing that I'm going to do here is I'm going to move on to building the mesh. So for this problem, I'm actually going to use an extremely fine mesh, because we want to capture that phase front as precisely as possible. So once I've meshed, I can actually move on to configuring the study. So for the study here, what I'm actually going to do is I'm going to set up a load ramp. Now, what I've defined in the phase change material here is a transition region. Now, the smaller this transition region is, the more accurate the solution is, but the harder it is to compute. So what I'm actually going to do is I'm going to start by solving for a large transition region, and I'm gradually going to make the phase transition sharper by reducing the transition temperature gradually. So it's going to start at 300, and the final solution will be 25 Kelvin. Okay, so that's me setting up my load ramp. And finally, what I'm going to do here is I'm going to activate adaptive meshing. So this will adapt the mesh that I've generated here based on the physics that I'm simulating. So in this particular problem, what I will see is it should adapt the mesh in the region where you have the phase change, because that's the region that needs the high resolution of the mesh. And in the other regions, it may coarsen the mesh. Okay, so I'm going to just hit compute on that. I'm looking at my time. I'm getting a little tight for time. So whilst that's computing, I'm actually going to come across here to a solved version of the model, which I have run earlier. So the model is set up identically to what I've described. And what you can see here is actually the adapted meshes. So this was the one that I initially built. I've got adapted mesh 1 and adapted mesh 2. So if I zoom in here, I can actually see in the mesh where it's refined the mesh, and this should correspond to where I see the solidification happening. In fact, let's move on and actually look at that. So here what I have is I have a plot of, let me just change this. I have a plot of the temperature. So if I plot temperature here, you can see the temperature distribution through the column. And what we would expect to see is that the material will be transitioning from phase 1 to phase 2 somewhere in sort of this region on the color bar. So we can actually go ahead and plot that. Okay, so I have it plotted here. So you can ignore the label on this plot. It's actually showing you now the phase. So what you can see here is that the blue region indicates where we have liquid. The contours show you where it's transitioning from liquid to solid, and the deep red indicates where you have solid. So you can see that below this line, we have had already quite a lot of solidification, and this is where it kind of exits the mold in this simulation. Now, what we could also do here is very quickly, I could set up a graph so that we can look at the temperature here at the center and compare it with the temperature at the edge. Okay, so by selecting some lines here and selecting a line graph, I can plot a variable along that line. And I'm just going to pick out the final solution, which is the last one I've computed here. So what we can see on this graph is we actually see that the higher temperature at the center of the column and the lower temperature where you have the cooling effect on the edge. And I could actually add on this a line to show us where the melting occurs so that we can actually see here where we get along the edges I've selected the cooling. So okay. Yes, okay. So this line here is indicating where the solidification occurs. So it happens very quickly on the outside of the column, but it happens much later at the center of the column. And as I mentioned, so this is now the model that I set up. It has computed. And here I have just a model where this has been extended. So what I've modeled is just a very much simplified version of this problem, but you could also look at modeling the full fluid dynamics here, as well as the heat transfer, and coupling these together within a single model so that you actually compute the velocity of the flow and the way that it flows, rather than prescribing that as an input to the model. Okay. So that concludes my demonstration. I'm going to hand it back to Ksenia, who's going to field your questions.
Thanks for great presentation, Robbie. So we're going to answer your questions now. The floor is open, and I already have seen a lot of questions. Thank you so much. So the first question is, can COMSOL solve problems that include moving meshes to update the shape of the geometry during the simulation?
Yes, so you can. So you can modify the shape of the geometry during the simulation. This can either be done by using a moving mesh, which is available here in definitions. So you can change the shape of the mesh, or you could actually use deformed geometry if you wanted to remove material. So we have a nice blog on our website about a laser ablation process where you actually change or remove material due to a laser process, and you deform the geometry and update its shape. So that could be added to the model using this deformed geometry feature here.
Thank you, Robbie. We're moving to the next question. If I have some measured material data, can I use that in my simulation?
You can. So where I was building my model here, I was just using parameters to define the material properties. So I've just defined these numerically. Now, you could use a function here instead to define these. So you could use experimental data, for example, and you could import that into an interpolation function. So this could, for example, be conductivity against temperature, or potentially Young's modulus against temperature. And then you could use this function to define the material properties. That could also be done using an analytical expression if you wanted to as well, rather than tabulated data.
Okay, next question for you. Is there any need to set the heat flux condition on the left side boundaries of this geometry?
To that question is no in this case, because of the rotational symmetry that I'm using. So although what we're looking at here is a 2D geometry, I'm actually modeling this as if it was a cylinder. So we're looking at the problem in cylindrical coordinates here. So what I'm actually applying when I'm applying the heat flux here on the boundary is the heat flux around this entire outside surface. So you wouldn't typically specify the heat flux at the center of the geometry, which is what you would do if you were applying it on the left-hand side of that 2D model.
Great, thank you. Are these models available for download?
So this model is available for download from our website. I believe it's called Metal Cooling. Also, the more complex version of this model, which is called Continuous Casting, is also available for download from our website. We have a number of other models that are available there as well, and a number of user stories as well.
Okay, great. So many questions. Next one for you. Some hint for friction welding processes where we have two materials in contact and one of them is at high speed rotation.
So I guess certainly the process could be modeled as a mechanical or thermomechanical problem. So you would need to, I guess, set this up as a contact problem where you're modeling friction between the two parts, and you would need to convert the frictional losses into a heat source. Now, rather than actually modeling the rotation of the upper part with respect to the lower part, I think it would probably be easier to apply a load to compress the two together and use maybe some analytical expression based on the rotational speed to generate a heat source, and then apply that heat source at the interface between the two different materials. Yeah,
Great, thank you so much. I hope we answered your question. Got time for a couple more questions. You mentioned apps. How do they work and how would we distribute them?
So what you're looking at here is something that's been built in the COMSOL Multiphysics user interface. To develop apps, you would typically click here and it will take you into the app development environment. Now we have a couple of simple apps, or not simple, sorry. We have a few apps that we've developed internally that you can see. So if I was to build, so let's say just open a tuning fork. So you would use the application builder to develop the app. I'm just going to open one very quickly here. So, and this can be done without using kind of any type of coding. You can actually design all of this using the mouse and dragging and dropping features and so on. And what you would end up with is something that's a standalone, well, not necessarily standalone, but something that is a simplified sort of user interface that you can interact with. Now, you can compile these apps so that they are standalone executable files and distribute these apps to colleagues or collaborators or whatever, or you can use a COMSOL server license to run these applications, where the server would be hosted on a network, and then you can access the apps over the network.
I think I can squeeze one more question. How can I check whether the magnetic field generated by a coil is affecting the state of the fluid surrounding it?
So I think if you wanted to simulate this process, you would need to derive a force of some kind, which is acting on the fluid that's a function of the magnetic field. So it would be a volume force, I expect. Now, to my knowledge, I don't think that there is a predefined multiphysics coupling that you could use for that particular problem, but you could probably implement something. Yourself manually. So that would be added here within the fluid as a volume force like this, which would be derived from the magnetic field. Okay.
Great, thank you so much, Robbie. That now brings us to the end of the Q&A. So any unanswered questions will be followed up after today, and sorry we didn't get a chance to answer all of them. Great question, thank you so much. So we do have a lot of additional resources where you can learn about COMSOL Multiphysics and what it can do for you. So if you would like to learn more about COMSOL Multiphysics and Application Builder in particular, you can access additional resources on our website. On the homepage, you will find a link to download Introduction to COMSOL Multiphysics and Introduction to Application Builder in PDF form, which contain all that you need to get started, including step-by-step tutorials and insights to setting up your model proposal or application. Also, as Robbie mentioned, on the website, we can find a regularly updated blog with a range of informative and useful information and user stories as well. So how other people use COMSOL Multiphysics, and then particularly in modeling manufacturing processes as well. COMSOL will be hosting our annual European conference in Cambridge, UK next year on 24th to 26th September. Please save the date. The registration will be open soon. It's a great opportunity to meet other COMSOL users, listen to keynote presentations from well-known organizations, and also promoting your own work by submitting your papers and posters. And also you will be able to attend panel discussions on various topics. And lastly, if you'd like to get in touch with COMSOL to ask any further questions about what you've heard today or anything else in particular related to your own simulation needs, you can do so at the link given on the slide. Additionally, there is a direct link on the website to request a live demo of COMSOL Multiphysics so you can be given a trial. Please fill in the very short survey to give us your feedback about today's webinar that will appear immediately after the webinar is finished. We do value your feedback. We'd like to hear what other webinar topics you will be interested in so we can deliver them later. So thanks again for attending our webinar. Thanks again to Robbie for great presentations, and have a great afternoon, everyone.